Okay, we're all live. So welcome to this reading group on random matrix theory. Hopefully the first and not the last. And so today we'll be talking about some of the basics of random matrix theory and especially one of the simpler laws. So like essentially we're talking about random matrices and distributions of random matrices, and more importantly, we care about what kind of distribution do the eigenvalues follow. And it's to some degree also the eigenvectors, but we'll see that there's less to say about the eigenvectors in general. But yeah, we'll be covering some essentially one of the simplest laws in random matrix theory called the Wigner matrices or the semicircle law for the eigenvalues. And yeah, to sort of state the problem, we have a matrix that the entries of this matrix are sampled from some probability distribution. In fact, it might even be a different probability per element. And so we have a matrix. We can compute its eigenvalues, and because it's also a random variable, we can also ask what is the distribution of these eigenvectors or the eigenvalues of this matrix X, and especially how does it behave as the size of that matrix goes to infinity. To some degree also, what do the eigenvectors look like? And for applications, well, it started out as something in physics to model essentially quantum systems, and roughly the idea in physics here is sort of the statistical mechanics approach of you have a very large system that in principles it is deterministic, but because it's so large, you can't really analyze it directly. So you just assume is probabilistic, and that somehow makes things easier. And that's sort of the idea, at least for physics, but for more machine learning focused interest, there are applications in statistics, especially whenever you're studying covariance matrices. For example, if you're doing like Bayesian estimation with multivariate Gaussians, then you have a covariance matrix that's randomly sampled, and you can use a distribution from random mixed theory to study that. In deep learning, there's a few papers studying either the spectral distributions of the matrices in the neural nets, so the linear components at initialization, because those are also sampled randomly, and as they evolve under training, they're technically still random variables. They just evolved from these initial ones, and so you can ask questions about what does the spectrum look like, and what does it tell you about whether your network has trained or not. So yeah, but right now we'll be just covering the simplest matrix distribution, and we'll actually be doing a bit of the calculations today because it's very instructive as to how you would go about taking a random matrix distribution that is not one of these simple ones and sort of derive yourself for example, the eigenvalue density. So I do have one slide so just a refresher about spectral theory. It probably won't be enough for all the complex analysis that we'll be doing, but it's a start. So for a matrix, or more generally a linear operator A n by n matrix, the eigenvalues are complex numbers lambda, such that this matrix here, lambda I minus A, so I is the identity matrix, this matrix here has to be not invertible. And so to find the as eigenvalues, you can use the characters equation, because if this matrix is not invertible, then it has to have a zero determinant. And if we explicitly compute the determinant, we get a polynomial equation in lambda that we can solve. At least for small matrices, we can solve explicitly, but then for large matrices, we have to solve it numerically. So there's always a degree of approximation in principle. Not in principle, but in practice, there's always a degree of approximation. And then if there is such a vector v in Rn such that A applied to v is equal to lambda v, that's called an eigenvector. And note that even though we're used to have matrices that always have a full set of eigenvectors, that is not always the case. There are some matrices that don't have a full set of eigenvectors, but for most of the nice ones, and especially the kind of matrices we'll be caring about today, we'll always have a basis of eigenvectors. And especially for symmetric matrices, so matrices such that they are equal to their transpose, so Aij is equal to Aji, there are two important properties. The one is that the eigenvalues are all real numbers, and secondly, we have an orthonormal basis of eigenvectors. So we can always find eigenvectors such that they form they're orthonormal, so that they're norm one and they're orthogonal with each other, and they have a full basis of our space. And this is so this makes these kinds of matrices some of the nicest to work with usually. So now we're actually talking about random matrices. So we've already sort of defined what a random matrix is, and so it is a probability distribution over matrices. And we can start by maybe taking like the probability density of getting each individual component, for example, assuming that the elements are separated independently. But another way to characterize or describe a probability distribution is through its moments. So I remember if like X is some kind of like univariate distribution, then the moments of X are the expectation of X to the kth power. And if you manage to compute these, usually they tell you about your distribution. For example, for k is equal to 1, you get the average value of your distribution. Using k equal 2, you can compute the variance and so on. So generally, if you know about the moments of your distribution, you know about you know essentially completely your distribution with some hand waving, but we'll ignore that. And for matrix distribution, okay, we might want to do precisely just the expectation of the kth power of A, but it's not so nice to work with. One, it's a very large object, it's still a matrix, it's an n by n matrix, and especially if we care about the limit as n goes to infinity, then it's not exactly clear what this should be. So taking simply this is not such a good idea, but if we take the trace of this object, so we define tau A as the normalized trace of our matrix, which because it's the trace, one property of the trace is that it's simply the sum of the eigenvalues, then that already tells us about the average eigenvalue. And generally, if we apply the trace to a sum function of A that returns a matrix, then we have the average value or the expectation of that function evaluated on the eigenvalue. So taking the trace tells us a lot about the distribution of the eigenvalues, not so much yet about the eigenvectors, but we'll see about that. So we sort of define, notice that we're doing the general physicist approach of assume that everything works, that the limits are well defined, and that we find solutions. And generally, we won't be worrying too much about whether they exist or not, as a proper mathematician would do, but I think that's for the better here. So assuming that this expectation here, or this normalized trace, has a limit as n goes to infinity, we'll be defining that as tau of f of a. And if, assuming that we can describe the eigenvalue distribution as having some kind of density rho, then we can also write this tau here as the integral over to the, in principle, this should be all the complex numbers, but in general, you have a smaller set over the density times the function. So standard expectation, expectation but relative to this eigenvalue distribution. Quick moment. So then we can now define the actual moments of a random matrix as simply these tau of the kth powers of A, and they're simply the kth moments of this eigenvalue distribution. So for example, if we take the first power, then that's the mean eigenvalue. If we take the second power, then that's if we do the calculation, that tells us about the Frobenius norm, so the sum of all the squared elements of our matrix. And so that tells us about the norm of our matrix, which is actually also very useful, and so on. Okay, so now we can actually talk about the actual matrices that we'll be talking about today. So Wigner matrix will simply define as an asymmetric matrix. So X is equal to X transpose with entries sampled from some normal distribution. And really, there are two kind of elements for this. You have the diagonal elements, and we'll assume that they're all sampled from a normal distribution with mean 0 and variance sigma d, or sigma d squared. And for the off-diagonal elements, right, because there's symmetry between the two sides here, we only really need to care about the upper triangle. And we'll say that they are also sampled from independently from the same distribution with mean 0 and variance sigma squared OD. And for now, like these, we have only two parameters, right? The diagonal variance and the off-diagonal variance. And they could be arbitrary, but there's a nice particular choice that is interesting. And if we sort of start computing the moments of this distribution, first of all, we get that the first moment is 0 because we're taking the expectation of just a sum of Gaussians that have 0 mean, so that the sum of Gaussians is also a Gaussian, and here we're just taking the mean of that sum, which is 0. So first moment 0, so the average eigenvalue is 0. That tells us that you should expect that our distribution is somehow symmetric around the origin. And then if we take the second moment, we obtain an expression that depends on n, as it does. And first of all, we see that really this, as n goes large, there's this n minus 1 times times the sigma squared OD, so the off-diagonal variance that dominates. So as n goes to infinity, really these diagonal elements are not so important. But one thing is that we want to be able to talk about the limit, uh, especially the limit of the density of eigenvalues as n goes to infinity. So we'd like to remove these n's here. And we'll do that by choosing our sigma, or variances. So sort of arbitrarily, we'll pick the off-diagonal variance to be sigma squared over n. And then for the second, the diagonal, we'll pick 2 sigma squared over n. And the reason for that is that this gives us something called the Gaussian orthogonal ensemble. So that ensemble in statistical physics and random matrix theory just means distribution. So you can, whenever you see the word ensemble in literature, you can just replace it by probability distribution and you're fine. It's mostly that anyway. And the reason we pick this one as 2 sigma squared n is that we can easily generate it as the sum of H plus H transpose, where H is just a matrix of, so just Gaussian samples, all sampled independently and with the same distribution. And right, because we're taking the sum of these, of the diagonal, it's the sum of two the sum of two independent Gaussians. So that's simply sigma squared over n. And then on the diagonal, because we're taking the same Gaussian twice, the variance is multiplied by 2 squared, so 4. And so we get 2 sigma squared over n. So far, so good. If we compute the third and fourth moments, well, the third is 0, and the reason for that essentially comes from the fact that the third moment of a Gaussian distribution is also 0, but then the fourth moment is equal to 2 sigma to the fourth. Now, you just need to trust the book on that one. The fact that this is 2 sigma to the fourth tells us already that this is not a Gaussian eigenvalue distribution, because a Gaussian, I think, is 3 sigma to the fourth for a Gaussian. So because the fourth moment is different from a Gaussian, we already know that it's not a Gaussian distribution for the eigenvalues. So that means you also have to figure out what exactly it is. By the way, don't hesitate to actually to interrupt for questions at any time, just in case. Okay, I mentioned that there's not much to say about the eigenvectors. The reason for that is due to this following property. So we'll say that a random matrix is rotationally invariant. Actually, we should be saying orthogonally invariant, so invariant under orthogonal transformations. So a random matrix X is rotationally invariant if the distribution of the matrix OXO transpose, where O is some orthogonal matrix, this amounts to changing the basis by expressing X as in the new basis given by the columns of this matrix O, right? Because an orthogonal matrix is equivalent to an orthogonal basis of vectors. And so this just amount to, yeah, rotating or changing the basis. And it's rotationally invariant if the distribution of this matrix, where we've changed or rotated the matrix or changed the basis, has the same law as X. So we have the same probability of observing this matrix as this matrix. Okay, the corollary of that is that actually the eigenvectors of X are in some sense uniformly distributed, in the sense that really between any orthogonal basis and one another, there's no difference. You have the same probability of having it. At least that's the case for symmetric X, which is the case here. More formally, if you want like a precise definition, we say that the eigenvectors of X, so that's a set of k orthogonal, n orthogonal eigenvectors, they are sampled from the uniform distribution on some manifold called the Stiefel manifold, which is in fact a manifold, like a differential manifold of orthogonal bases of some vector spaces. So this is nice because in practice, what this tells us is that if we have a random matrix with this property, we know that the eigenvectors are trivial in some sense. Like there's not much interesting about the eigenvector. We have the same probability of getting one. So that means that really only interesting thing is in the eigenvalue distribution.
Are there any like random matrix ensembles that don't have this property with the eigenvectors? Or is this kind of like a, I don't want to say universal property because that means something else, but is that just like, yeah, I don't know. Is every interesting and or tractable matrix ensemble uh, invariant to orthogonal transformations?
So tractable, I'm not sure yet, but one thing you can imagine, so as we'll see later, indeed the Wigner matrices are rotationally invariant.
Mm-hmm.
One interesting to me at least family of random matrices which is not so rotationally invariant is whenever you sample a random graph. So for
Hmm.
example, if I have a random graph sampled as xij equal to some Bernoulli of probability p,
Mm-hmm.
and suppose it's symmetric and that the diagonal is all zero, so this is a random matrix, but because it's a graph, it has to stay a graph, and so it's invariant under permutations, but it's not
Hmm.
invariant under orthogonal. So because so in some sense you could say invariance under permutation for a statistician, it's essentially it's an exchangeable family of random matrices because
Mm-hmm.
it's invariant under permutations, but it's not orthogonally invariant. And I think I've been thinking about this morning because that's one thing I might try and compute, but that means that at least for random graphs, the eigenvectors are not uniformly sampled like this. It's more like a discrete distribution on the Stiefel manifold.
Gotcha. Cool. Thank you.
Okay, so as we've alluded to, these Gaussian orthogonal ensemble are the Wigner matrices that are all rotationally invariant. And the way to see that, uh, first of all, recall that if you have a multivariate Gaussian vector V with some sample like this, so zero mean and um, uniform, uniform covariance matrix, this is rotationally invariant because if we define W as OV, where O is again an orthogonal matrix, this is also this has the same distribution as V. So that means that when we take our matrix H to construct the Wigner matrix and we multiply it with O, that means we're just multiplying every column or every row of H with O, and so we have vectors or vectors of independently sampled Gaussians like this. They're rotationally invariant, so they have the same distribution. That means that OH has the same distribution as H, and OH O transpose also has the same distribution as OH. And so if we put everything together, that means that OX O transpose has the same distribution as X, and so the Wigner matrices are rotationally invariant. So the eigenvectors are not super interesting. Another way to see it is to explicitly compute the the density of getting one particular set of xij's because they're sampled independently. It's a joint distribution, and if you do the calculation, okay, we get this normalizing term times an exponential of this big expression, which we can rewrite as simply the trace of x squared. And so we get something that is proportional to the exponential of a trace of a function of x. And because the trace is also one property of the trace that it is also invariant under these change of basis, that means that anytime we have, so first of all, this expression is very invariant under this change of basis, so the probability is the same, so same thing. And more generally, if we have a probability distribution like this that looks like the exponential of some trace of some arbitrary function of our matrix, this will also be a rotationally invariant matrix. So it's more of a general formula for random matrices that are rotationally invariant. So yeah, from now on, we won't be talking too much about the eigenvectors because they're not super interesting. Which leaves us to the meat of this present session here, which is deriving the eigenvalue density of the Gaussian orthogonal ensemble. Short version, it's equal to this, called the semicircle law, because if you plot this on a curve, get a function that is only non-zero between -2 sigma and 2 sigma. And in between the two, it's essentially a half circle because this is essentially the equation of a circle. So that's why it's called the half circle distribution. And we will take the time to derive it explicitly and doing a couple of more steps than in the book, mostly because it's actually very instructive if you wanted to do this kind of derivation for another kind of random matrix that you care about. A word of warning, this may contain or almost surely contains complex analysis and physicist techniques, so yeah, strap yourselves in and ask questions if you're confused. Okay, so I guess no questions so far. First of all, so I alluded a little bit to it when defining the eigenvalues or reminding people about the eigenvalues a little bit earlier. So a standard tool in spectral analysis, maybe not so much whenever you're in the finite dimensional case, but in infinite dimensional case, that certainly is useful. It's called resolvent. So if you have a matrix a square matrix, the resolvent is defined as the inverse of this z minus zi minus a, where z can be any complex number. And by definition of the eigenvalues, we know that this function is not defined on the eigenvalues of A, so on the spectrum of A more generally. Okay, so this is still a matrix, but if we take the trace, that gives us something called a Stieltjes transform, or the normalized trace, so 1 over n over the trace of the resolvent, by properties of the eigenvalues and the eigenvalues of an inverse, we know that it's simply the normalized sum of 1 over z minus the lambda k. So this is a function that takes a complex number z and returns another complex number z. So this is a complex function. And so to study it, we'll use complex analysis. And we know already that whenever z is equal to one of these eigenvalues, the function seems to diverge, right? So I'll show you a plot of what one of these looks like in a moment, but I'll briefly, before we do that, we have a nice property about the resolvent, which is that for a large enough z, specifically if z is larger in module than the norm of A, here the norm might be the operator norm, but not worry too much, just take z large enough, then we can use something called the Neumann lemma to explicitly compute this inverse matrix. We just need to factorize it a bit, so we extract 1 over z and I minus 1 over za. And whenever we have something like this, by the Neumann lemma, we know that it can be written as the sum or the infinite series of the a to the k power over z to the k. And so the resolvent is simply equal to, at least for z large enough, to 1 over z times this infinite series. We'll see in a minute why it's nice, but at least it means that for large enough z, this function is well behaved. Okay, so now let me.
What happens if the z isn't large enough? What happen like
Good question. Then you have to do some more advanced complex analysis, and you may suffer a little bit. Okay, so I have here, so it's a dual notebook, but you could easily do this in Python as well. So I'm here generating a random Wigner matrix, and I'm plotting this Stieltjes transform of that matrix. And roughly, so this is a plot of the complex module of that function in the complex plane. And you can see that it's basically a bunch of spikes. These are the eigenvalues, and as we get closer, we see that it seems to be getting a little bit messy, right? And notice that the eigenvalues, because it's a symmetric matrix, they're all clustered on the real axis, and because we saw that the distribution has a compact support, that they're all in this nice interval. So we'll come back to this in a moment. I think maybe there was about to be a question. I saw some movement in chat. Maybe not. I guess we'll see. But yeah, at least as far as you should be concerned, this Stieltjes transform is just a tool to study the spectrum of operators. Okay, so because we're also working with random matrices, we want to talk about the density of these eigenvalues, and for whenever you have a empirical sample of a distribution, you can talk about the empirical distribution or empirical density. Here for the spectrum is simply 1 over n times the sum of these Dirac deltas, so a function that essentially only equal to infinity or equal to 1 when the argument here is 0. So basically this just only gives us a little blip at the eigenvalues. But we can write it as this integral here. Okay, so far so good. So by this Neumann-Lemma property that we saw earlier on the previous slide, we know that this so empirical Stieltjes transform has to converge for z large enough to this thing here equal to the series from k to 0 to the infinity of 1 over z to the k plus 1 times the trace of the k power of a. Now, again, some hand waving, assuming that this 1 over this normalized trace actually converges to the expectation, so the tau of AK, so the moments of A, we expect that this empirical distribution should converge to some well-defined limit simply equal to the series of 1 over z to the k plus 1 times the moments of A. What this means, at least for our purposes, is that this limit g of z contains all the information about the spectral density, at least in the limit, because it has all its moments. And because we said if you know all the moments of your distribution with some caveats, you know your distribution. Okay, so why are we doing this? Well, right, our goal is to go from this empirical distribution to this limit or asymptotic distribution, but there's no clear way to do that. So what we'll do is that we'll go around this problem by first going to the Stieltjes transform, finding an expression for the limit g of z using a typical physicist technique of just setting up your equation and assuming it works. So specifically, we'll be setting up a recurrence relation between the the Stieltjes transform for n and n size matrix and Stieltjes transform for n minus 1 matrix. Take n to infinity, that gives us a fixed point equation for g. In physicist speech, that is equivalent to something called the cavity method or the self-consistent equations. You can tell that the physicists are really good at naming things because definitely that's what cavity method tells me. Um, and then we'll use a formula called the Stieltjes inversion formula. We'll see that in due time to then go from this limit Stieltjes transform back to our limit eigenvalue density. So that's the general approach, and we'll be doing that explicitly. Okay, everyone good so far? Okay then. So let's yeah get into the thick of it. So first, let's take a Wigner matrix and define M to be Z times the identity minus X, so the thing that we'll try to invert for the resolvent. And then we need to use a formula from chapter 1 of the book called the Shor complement formula that gives you a way to express the inverse of a matrix by cutting into blocks. So specifically, we're taking n, we're taking the first element m11, and then we're cutting into blocks. So we have a block m22, which is a n minus 1 times n minus 1 matrix. You can see the recursion coming in. And then we have the row and column here. That's from the leftover elements. And the Shor complement formula tells us that 1 over the gx, so the first element or the inverse of the first element of the resolvent is equal to this formula. So we have the first element minus essentially the inner product of, yeah, so this row vector times the matrix times the column vector here. And then, or the inverse here. Okay, so we have an expression over for this. Notice that this M11 element, it has expectation z, right? Because x has expectation 0 plus z times I, so the expectation is z. Then notice that these mi's here and the matrix here are independent. So we can just take the expectation over the x1i's. to just get an expression of the inverse of M22. And because it's the expectation of over some Gaussian vectors, it becomes simply sigma squared over n times the or M22II and some delta. Don't worry about it. That means that the expectation of this sum, right, this part here, that simply becomes sigma squared over n times the trace of the inverse of this matrix here. But this matrix here, it's the inverse of another Wigner matrix, or it's the Stieltjes transform of another Wigner matrix, and so recursion coming in, it's simply that this 1 over n minus 1, that's the Stieltjes transform of a Wigner matrix of size n minus 1 and variance sigma squared n minus 1 over n. Take the limit as n goes to infinity, that converges to g of z. So our hopefully well-defined and meaningful limit for the Stieltjes transform. So that means that this thing here should also have a nice limit. This thing has a nice limit. This thing has a nice limit. So the last point is this 1 over gx. So gx11. Again, using some hand waving, we'll say that it approaches a deterministic limit as n goes to infinity, and specifically it does it nice enough in a way that's nice enough that we can say that the expectation of 1 over gx11 is 1 over the expectation. That's not true in general. Don't do this at home, kids, but at least in this case it works. And using rotational invariance, which implies, among other things, invariance under permutations, we know that really, okay, we have one diagonal element, but really all the diagonal elements have the same limit in expectation. And so we know that the expectation of gx11 is simply 1 over n times the expectation of the trace of gx, which by definition is the expectation of the Stieltjes transform, which, as we are assuming, is converging to G. So if we put everything together, right, we have 1 over G of Z that is equal to Z minus sigma squared G of Z. And we have an equation for G that we can try to solve. In fact, if we rework it, manipulate it a little bit, we get a quadratic equation that we can solve for G, and that tells us that G of Z is equal to Z plus or minus this square root of Z squared minus 4 sigma squared divided by 2 sigma squared. Notice that we have two solutions, so we have to pick the right one. We'll see about that later. To do that, we'll be extracting this Z squared here out to get something a bit nicer. And the reason it's nicer is that it also tells us that this solution here, as Z goes to infinity, it's about equal to 1 over Z, which is consistent with what we know about the behavior of G of Z as Z goes to infinity, that it should be equal to the approximity series. So we have only 1 over Z terms, so it's consistent. If we're taking the positive, so the Z plus Z and so on, that wouldn't be the case. So that way we can eliminate one of these solutions. But actually, we'll see the plot of this function in a minute. So this is a complex function again. We know its limits, and as a sketch, it looks something like this. Beyond the circle of radius 2 sigma, it's analytic, so it's essentially this expression here. The function is well behaved, we don't need to worry about it. Within the circle, it's a bit more difficult, and even more difficult is along this line. In fact, along this line, this function is singular, so this series expansion does not work. And really, it's not well defined what happens to the function along this little interval here. Now we can worry a little bit about how does the conversion of these empirical Stieltjes transform look like? Because, right, it's a sum of 1 over z minus lambda k, so it's just like a bunch of spikes. How does it exactly does it convert to something that has like a continuum of singularities? Again, this is complex analysis. If you don't know it, don't worry too much. But yeah, we're talking about weird functions. And roughly, the idea is that these poles here, we can approximate it as n goes to infinity as just Dirac delta functions, and then g of z becomes an integral of these of the density over z minus x over the support of g, which should be probably this little segment here. But I think we know that already. Okay, so far so good. So let me actually show you what this function looks like. Whoop, one moment. So this is the analytical limit. So notice here that it looks a little bit weird because we have two parts. One which is on the negative um, imaginary part and one on the positive. Ignore what happens here, right? It looks weird. But really the part we care about is this one on the bottom. So for numerical approximations that we'll see in just a moment, we'll be using this part of the function. So you can see that this is a bit of a nasty function, and we can see that along the real line, it looks a little bit funky. I think especially, yeah, it should be around 2, so be careful there. Okay. Ah, of course, I had the wrong button. Okay, so one thing we'd like to do is approaching our density using our Stieltjes transform. And one thing to notice is that if we take z is equal to x minus I theta, where x is in the support of our distribution, so part of this little interval, and we take eta to be fairly small, but not too small, we see that we can compute it explicitly and find that it looks something like this. And if you squint about it or squint at it for a little while or just trust the book on this one, this is essentially a convolution of our empirical distribution with this function here called the Cauchy kernel. And because the Cauchy kernel, it's a convolution, so we're integrating this thing here with this function here. And because this function here is mostly sharply peaked, so it's mostly concentrated around 0 and then goes quickly to 0 on the outside. It means that this integral is mostly going to capture points that happens in this part. So only here the eigenvalues here. That means that if we take our eta way too small, and especially smaller than 1 over n, this integral is only going to capture like 1 or maybe 0 eigenvalues. Okay, so yeah, good run. I guess you'll have to see the recording. So if we take eta too small, we only have too few eigenvalues that contribute to this convolution, and so it will fail to converge to anything meaningful. And so if we take on the other hand something maybe around 1 over the square root of n, then we have a lot of eigenvalues that contribute to this integral, and so we get a better approximation. But I think this will be clearer if I pull up the diagram here, right? So we're taking this function here, and we're looking at slices as so like if you imagine this horizontal line moving around. That's the line x minus I eta, and we're taking eta closer and closer and closer. Now this is the analytical one, but if we take this one, so let me zoom over a little bit. Right, we're getting closer and closer to this function, If we get too close, then we end up in the spikes, and so we like it, yeah, yeah. In the spikes, it's a bit wonky. If we go close but not too close, let me try and pull it up. Then we should be able to get something that looks a little bit like the density that we try to approximate. So that's the rough idea. Now, even so, and actually let me show what this looks like in practice. So doing exactly this process of taking eta to be 1 over n 1 or 1 over the square root of n, and we're looking at not the module as the plot above shows, but just the imaginary part of the Stieltjes transform. So we see, okay, it's a bit hard to see, but the analytical one is just this half circle. This purple line is when we're taking 1 over n, where it's way too close to the eigenvalues, and you see that it's really spiky. If we take 1, we're way too far, and so it's not even close. But if we take around 1 over the square root of n, then let me get the 1 over n out. Yeah, much better. We can see that it sort of sticks closer to the curve, and so that's a decent approximation. I think, yeah, you can even look at the error as a function of eta. You can see that, okay, if you get way too close, the error is super large. If you get further away, again, it's super large, and then roughly 1 over square root of n is close to the minimum. So generally, 1 over square root of n is what you should go for. Okay, now more generally, so we can expect that, and this is essentially the Stieltjes inversion formula, is that if we take the limit as eta goes to 0 of this x minus I eta, we get something proportional to pi times the density rho of x. And so if we do that for the Wigner distribution, we get that this converges to this thing x minus x squared minus 4 sigma squared was 2 sigma squared, and we only care about the imaginary part, and so the only way this has an imaginary part if this term here is imaginary, so we need x squared to be smaller than 4 sigma squared, and so the imaginary part will be equal to square root of 4 sigma squared minus x squared over 2 sigma squared pi, and remove the pi and we have the eigenvalue distribution rho. Might have missed. I thought I missed a slide, but anyway. Okay, so that's how you can compute the eigenvalue distribution. Briefly, so a bit beyond the Wigner matrices, so we've seen the Gaussian orthogonal ensemble. There are two other families of similar matrices, namely the unitary and symplectic ensembles. Basically, they are what you get when you replace the real numbers for your Gaussians by complex numbers. So a complex Gaussian is simply the sum of a complex number with the real part a Gaussian and the imaginary part a Gaussian. And for the symplectic, you use quaternions and do the same thing. Again, same setup, normally distributed entries. And in fact, they all have the same eigenvalue density, so the half circle. The only difference is for the eigenvectors, so the Gaussians, or for the orthogonal one, they're invariant in the orthogonal transform, the complex one under unitary transform, and the quaternions under symplectic transform. Don't worry about what a symplectic matrix is. We generally won't be talking too much about the quaternions one. Now, almost to the end, another type of random matrix you can care about if we drop the symmetry constraint. And for example, if we just take a matrix of independently sampled Gaussians, then the eigenvalues of that will follow something called the Gurko circular law. simply that means that the eigenvalues will be uniformly distributed in a circle, and then that's for maybe for next time. The Wishart ensemble, if we take the product or the product H times H transpose, where H again is it's just a matrix of independently sampled Gaussians, and we look at the singular values of that, then it's something a little bit like the half circle theorem, the half circle um, law, but only over a quarter circle. But I think this deserves some better uh, plot. So this is the circular law. So I'm sampling a matrix, not the symmetric, and taking the eigenvalues. And you see that they seem to be filling out this circle pretty nicely. Notice though that even though I haven't really mentioned it, but even though we're talking about the distribution of the eigenvalues, it's important to notice that the eigenvalues are not independently distributed. And for example, in this case, you can see that it's symmetric around the real axis simply because it's still a real matrix, and so a real matrix will only have pair of conjugate eigenvalues. And if I take then the same idea but for complex entries, then it's really fully non-symmetric, and it still fills out the circle. But generally, and this is sort of alluded to in in the exercises for the first chapter, or in the video if you saw it, is that the like we're talking about the distribution of the eigenvalues, but for a given matrix, the eigenvalues are not independent; they're sampled together, and we can see that also by looking at the spacing distribution between the eigenvalues. So specifically, this is again for a Wigner matrix. If we look at like the space between any two consecutive eigenvalues, and we look at the distribution of that, we see this sort of peaked distribution. It's possible to derive it exactly, and I think it's just a linear term times a Gaussian, but notice that at zero it's equal to zero. That means that it's almost impossible for any two eigenvalues to be exactly the same or very close, and really we seem to be that the average distance between any two eigenvalues is about 0.03 here. Okay, I'll go back to this question, but actually there is already a Julia package for this thing, I think. Yeah. Um, Briefly speaking, if it were independent, then we'd have something following an exponential distribution. So this is part of the exercise of the book that of sampling it, assuming it were independent, and observing this exponential fit that is not what we observe for these matrices. So do remember that the eigenvalues, because they're sampled together for a given matrix, that means they're not independent. And with that, I think that was it. So I hope people enjoyed it. And are there any more questions? Okay, but yeah, for maximum livelihood, um, as I can send you over DM, but there is a Julia package for matrix distributions already. So the exercises in the book are not in Julia. I made these for myself to do the exercises. I think the book just tells you to use your favorite programming language to do the exercises and doesn't specify any specific language. But I did them in Julia because, of course, like I wasn't going to do them in MATLAB. Do you really need an excuse to use Julia? Come on. But yeah, I'll post the slides and the code on on the repo of the reading group. I think also I forgot to post the slides last time. But yeah, any questions or any other questions besides stuff about Julia? Apparently not. So yeah, I think that was it for today. Maybe a little question. Let's see. No. Um, yeah, then I don't think we have a clear idea what we're going to do next. I think maybe Nev, you wanted to do the next one on uh, geometric algebra transformers. Are you still up?
Yep. I'm going to try to get a presentation in the next week.
Okay, cool. Then yeah, next week we will cover that. So I'll handle the scheduling and so on. So yeah, thanks a lot. So yeah, then we can leave it at that for today. Thank you for all for coming, and I hope you enjoyed the visualization and my explanations. And hopefully this won't be the last time that we talk about random matrix theory.